How do telescopes help us learn about the universe? This is a Galileo scope, a modern version of the telescope first used by Galileo just over 400 years ago to open up our view of the universe. Any telescope is governed by its diameter, and bigger is better. Larger telescopes collect more light, and they also deliver sharper images. We're going to learn how larger and larger telescopes give us sharper and sharper views of the universe, and also more distant views of the universe. Modern telescopes now are 8 or 10 meters across as compared to the inch of this telescope. We'll also learn about how telescopes can be used not only in visible light, but in invisible wavelengths such as ultraviolet, infrared, and radio to collect information about the universe. Here you can see the history of optical telescopes over the last 60 or so years. At the top is the Palomar 200-inch that was the largest in the world for decades until a renaissance in telescope building in the 1980s and 1990s. See the cluster of large 8 and 10 meter telescopes that were built around that time. At the bottom you see the huge telescopes being imagined or planned. On the right you see the corresponding growth in the size of space-based telescopes, and it's much more modest because it costs an awful lot more money to launch something into space. The Hubble Space Telescope, if you made a list of the world's largest telescopes, wouldn't crack the top 50. But space astronomers are hoping for the James Webb Space Telescope, which will bring space astronomy to the level of the large telescopes on the ground, with a 6.5 meter mirror that unfurls in space 1,000,000 miles from the Earth. Here we see historical comparisons which show that the cost of major ground-based facilities have not changed that much over a century and a half. Turned into modern purchasing power, the largest telescopes in history have always cost about $1 billion, and the 20 and 30 meter telescopes being planned right now are coming in around $1 billion. That sounds like a lot of money, but in fact to put telescopes in space costs even more. By most accounts, the Hubble Space Telescope over the history of its mission has cost somewhere between $6 and $8 billion. Astronomy does not come cheap these days. Astronomers and engineers have had to play some interesting games to continue to attain new sizes with telescopes. If you look at the history of telescopes since Galileo, you'll see that it's actually a logarithmic or exponential progression. Telescopes have been increasing in size over 400 years in an impressive way. But if you project from the 10-meter telescopes of the 1990s, it would seem to take a half century to get us up to 40 or 50 meters. This time curve is accompanied by a cost curve that is also rather brutal. These large telescopes cost an enormous amount of money. Astronomers have had to use innovation to continue to increase the size of the largest telescopes. The two figures of merit of any telescope are both determined by its aperture or diameter. One is fairly obvious, the collecting area, which goes as the square of the diameter. The other figure of merit is angular resolution, or the smallest detail that can be observed in angle on the sky. That's important not only for resolving features, say, on a planetary surface, but also for working in a crowded region like a galaxy or star cluster, seeing finer and finer detail and fainter objects. The angular resolution of a telescope is just as important as the collecting area. Ground-based telescopes are limited in resolution by the blurring effects of the Earth's atmosphere. Here's the relationship between angular resolution, the wavelength of radiation being used, and the diameter of the telescope. You can see that the larger the telescope, the smallest the angle that can be resolved, so bigger is better. Also, it's proportional to the wavelength, so shorter waves deliver higher angular resolution, or more detail. Also, you can see it takes a large telescope to deliver a very small angular resolution. But that blurring of light caused by the Earth's atmosphere limits the utility of ground-based telescopes. Essentially, any telescope more than about half a meter in diameter is limited not by its optics, but by the blurring effects of the Earth's atmosphere. This is a major limitation that astronomers have worked hard to overcome. There are two classic types of telescopes. One is a refractor, familiar from the Galileo scope and from Galileo's original device. This typically involves using two convex lenses contained in a tube to make an image. But it has serious problems as far as frontier research in astronomy go. The lenses have what is called chromatic aberration, where images of different waves of light are not formed in the same location, so you cannot bring the red and the blue light from a star or a galaxy to a focus in the same place. Also, as you scale this telescope larger and larger, the length of the tube becomes extremely large, and the mass and weight of the telescope cause it to flex, which is a problem for image stability and quality. So, in practice, no telescope larger than the Yerkes 39-inch has ever been built and used for research. Essentially, refracting telescopes are no use for current research in optical astronomy. The first reflecting telescope design came from Isaac Newton and has barely been improved upon in that time. The basic design seen here is that the light comes in, is bounced off a primary mirror, and then a secondary mirror, and usually returns through a hole in the primary mirror to a focus below the telescope. This folded design makes the telescope more compact, usually much shorter than an equivalent-sized refracting telescope. It also allows the heavy instruments that astronomers tend to use to be positioned under the telescope, counterbalancing it and making it flex less. This is the design that's used for all the 4-meter and larger telescopes at the world's major observatories. Here you can see the first two large telescopes built in the 10-meter class. They're the Keck telescopes. They were actually funded by the founder of Superior Oil, the 7th world's largest oil company. He was looking for a way to transfer his wealth to his sons and avoid taxes, so he gave a donation that ended up being $300 million to Caltech and the University of California system to build twin 10-meter telescopes. They're located in one of the preeminent sites for observational astronomy, Mauna Kea, a dormant volcano on the Big Island of Hawaii. Here you can see inside one of the Keck telescopes, and you'll see that it's not a single mirror. It's a mosaic of 36 hexagonal elements, each 1.8 meters across, and you can see someone sitting at the focal plane of this telescope at the central hole. These mirror segments are kept aligned by a laser actively because as the telescope moves around the sky, it flexes and changes shape subtly, altering the images. So it must be actively controlled the entire time of observation. We've learned that the power and quality of a telescope is determined by one thing, its aperture or diameter. The collecting area goes as the square of the aperture or diameter, and the resolving power goes as the inverse of the diameter. We've also seen that the original telescope design of Galileo is not the design used in most major astronomical observatories. Telescope building has moved towards reflecting telescopes that bring their light to a focus underneath the telescope. And we've seen an example of one of the world's largest telescopes built with this design.